session. If you want to go back and rewatch some of the stuff that I talked about or get a little bit more of an explanation later on tonight or sometime tomorrow, you will be free to do so. So I'll make sure to post the video of the class as soon as I can after class is over. All righty, so where are we going? There we go. All right, so we are in week 2 of our physics class. So we're done with week 1 now. We're moving on to week 2. And so today, like I was saying earlier, we're going to get a little bit more into kind of ideas of what are some different things that people that study physics measure or calculate or are interested in. And at the end of week 1, we're talking about the laws of motion and how physics is used to study how things move. So today we're going to look at exactly how physicists calculate different ways that things move. So we're going to look at notes that deal with speed, velocity, and acceleration. And even though these all sound like really similar and kind of the same thing, in terms of physics, these are actually related but separate quantities, separate things that can be measured in order to get an idea of how the motion of a certain object might be changing. So there are a couple things that I'm planning on having us hit on today. I want to go over with you guys, how is it that we can describe motion? So when things move from one place to another, what are some of the different ways that we can describe how they moved? We're going to compare and contrast speed and velocity. They are very similar, but not the exact same. And we're going to talk about how that is. And then we're going to talk a little bit about acceleration, what exactly acceleration means in the context of physics. So speed, velocity, acceleration, it all has to do with motion, how things are moving. And the thing about motion is that it is relative, meaning that if you want to compare how fast or how slow something is moving, you have to compare it to something else. Think about it as if you're on like a train going through the landscape, and you can probably tell from the inside that the train is going really fast because you see all the trees and the bushes and stuff whipping by the train, right? So these reference points are telling you that the train is moving really fast because the train and the tree are going by each other really quickly. Sometimes if there's one train on one track and the other train on the other track, and they're both going about the same speed, it can be hard to tell how quickly they are moving because in relation to each other, they're not moving very much, right? Or think about if you're ever driving on like I-35 or 183 or something like that here on Austin, your speedometer on your car says that you're going 60 miles an hour. But if you look at the car next to you, it's sticking with you pretty closely, right? So compared to the ground, you're traveling across the ground at 60 miles an hour. But compared to the car next to you, you're not really moving all that much. So motion all depends on what sort of reference point that you're dealing with. For the most part, most of the motion that we're going to be looking at is considering like the ground or some sort of stationary object as the reference point. So we're going to be looking at like the total speed or the total distance as things move across the Earth. So one way that we can measure movement is the distance that an object travels. When something moves, it goes from point A to point B, it traveled some sort of distance. So in SI units, in scientific units, we don't use like feet or miles. We use things like meters and kilometers. A meter is pretty close to a yard, and a kilometer is about a little over half a mile. It's like 0.6 of a mile. So distance is just how much ground an object has covered. If your odometer on your car says 15,000 miles, and you leave your driveway and you drive around Austin for a little while, and you come back and park in your driveway, your odometer has probably gone up to like 15,036 miles or something like that, right? Distance is just the total amount of ground covered. We have our little car that has gone from A to B. So it's covered some sort of distance in between. So distance is pretty straightforward. It's probably what most people think about when they think about things moving. It's like, yeah, you just measure how far it moved in all its directions, and that's the distance that it covered. All right, when people run like an 800-meter race at the Olympics or something, the track that they're on is, I want to say, a normal like track and field track is like 200 or 300 or 400 meters. So they have to do a couple laps around the track in order to cover 800 meters or 1,000 meters, right? So in order to get that total distance, they need to go around a couple times in order to cover that much ground. So another way that we can think about how things move, other than just thinking about distance, is something called displacement. So displacement isn't just the amount of ground covered by an object. It is the total overall change in that object's position. All right, so in this example here, we have our house, which is down here at this block. And then you leave the house and go to school, which is up here at this block. On the way to school, you take these roads. You go a mile this way, a mile up this way, 2 miles up this way, 3 miles up this way in order to get to school. So your distance is 1, 2, 3, 4, 5, 6, 7, right? You cover a total of 7 miles on your way to school. However, in a straight line, the school is only 5 miles away from your house. So if you were to take a giant ruler and measure directly from your house to your school, it's only 5 miles, even though you traveled 7 miles in order to get there. So this displacement is how far away is your ending point from your starting point, the overall change in your position. So while you may have had to drive or ride your bike 7 miles in order to take the roads to get to school, the actual displacement from your house to your school is only 5 miles. The other important, really important thing to note about displacements, make sure to pay attention to this. If an object goes and moves around, but ends up where it started, that means that the overall displacement is 0. Nada. So like the example I was talking about earlier, where you drive your car all around Austin and then come back home and park in your driveway, your distance might have been 30-something miles, but your displacement is 0 because you started at your house and you ended at your house. Same thing here, where when you walked to school, you took the roads in order to get there, but then when school was out, you left and jumped through the parks and jumped through some people's backyards and came straight back home. Your overall displacement would be 0 because you started at your house and you ended at your house. So displacement is this overall change in position. How far away is your starting point and your ending point? Distance is how much ground that you covered. How much distance did you travel going between the starting point and the ending point? Sometimes the distance and the displacement are the same. So if you travel directly in a straight line for a little while and then stop, your distance and displacement will be the same. However, usually they are different. Usually the direct space between where you started and where you ended is not the exact same as all the roads that you had to take in order to get where you needed to go. So this is the first big thing that I wanted to go over. This difference between distance, which is just overall how far did you travel during your journey, and displacement, which is what is the difference between your starting point and your ending point. What is your overall change in position? All right, so that's a really important concept to kind of have down. So does anybody have any distance or displacement related questions so far?
No, sir.
All righty. So distance, how much travel you did. Displacement, how far you ended up from where you started. So both of these tie back into speed. So speed is, in physics, it's something called a rate, meaning that it is a change over time. So your speed is some sort of change over that happens in a certain amount of time. And in physics, when things happen in a certain amount of time, we call them rates. So speed is your change in distance. How much distance that you covered over how much time it took you to cover that distance. That will tell you how fast that you are going. So in your car, you might be used to things like miles per hour. So distance over time, miles over hour. In physics and in science, we use things like meters per second or kilometers per hour. So same general idea, just different units. So if you ever see this like M-S or M per S, that means meters per second. So if you want to calculate somebody's average speed for a certain trip, then we have this handy dandy simple formula right here. So there are going to be a couple different formulas that we go over today. This is the first big one. Speed is equal to distance divided by time. So if you know how far somebody traveled, their distance, and you know how long that it took, time, then you can do this simple distance divided by time calculation in order to calculate somebody's average speed for that trip. So, for example, if I managed to travel 500 meters in 5 seconds, then my average speed would be 500 meters of distance divided by 5 seconds of time, which would give me 100 meters per second, which is pretty fast. So distance divided by time will tell us our speed. Now, because this is such a simple little equation, we can also rearrange it in order to find out some of these different values. So for speed, if you know the distance and you know the time, you can do distance divided by time to get speed. If you know your average speed of an object and you know how long that object was traveling at that speed, you can calculate distance, right? If something was traveling at 3 meters per second and it was doing that for 10 seconds, then we could do speed times time, 3 times 10, and figure out that we traveled 30 meters in that time. right? If somebody travels 120 miles and it took them 2 hours, then you know, oh no, that's all right. If somebody was traveling 60 miles an hour on a 2-hour road trip, then they covered 120 miles. So if you know the speed and you know the time, you can do speed times time, that's hard to say, speed times time in order to figure out the distance traveled. And then finally, if you know how far somebody traveled and you know how long that it took them, or you know their speed, you know how fast they were going, you can calculate time. If somebody traveled 100 miles and they were doing an average of 50 miles an hour, then you'd expect it took them about 2 hours. 100 divided by 50 is 2. Distance divided by speed equals time. So both of these are just based on rearranging our basic speed calculation up here. So speed you can calculate if you know the distance and you divide that by the time. Distance you can calculate if you know the speed and you multiply it by the time. And time you can calculate if you know the distance and you divide that by the speed. And again, this is just average speed for somebody's entire trip. Speed equals distance divided by time. How far somebody went divided by how long it took them will tell you their average speed for that trip. So if you know the distance that an object has traveled in a certain amount of time, you can calculate speed. So again, this is average speed. On average, how fast were they going over this time? There's also instantaneous speed, which is the thing that like your speedometer is saying as you're driving down the road or as you're driving down the highway, right? That's measuring your actual speed at that exact moment, whereas our speed formula down here on the bottom left is just giving us somebody's average speed for the entire trip. So instantaneous speed, you can only really figure out if you're traveling in a vehicle that has a speedometer, or you have like one of those like police radar guns that tells you how fast something's moving. That can also tell you instantaneous speed. If you're using our formula that we just talked about, that means that you're just calculating the average speed of that object. All right, any questions about speed so far? Anything that they want me to go back and explain some more?
A week, but other than that,
No, sir.
Completely.
All right, great. Thanks, Annalisa. So speed, distance over time tells you how fast that somebody was going for certain trips. So speed is just how fast that something is moving. Velocity, on the other hand, is a little bit different. Sometimes people get confused and they think velocity and speed are the same thing. But velocity actually describes two things. Speed is just how fast something is going. Velocity is how fast it's going and what direction that it's going in. So if you leave your house and you turn right onto the road, you're going to have a different velocity than if you leave your house and turn left on that same road, right? Even though you might be going the exact same speed, you might have pulled out of the driveway at the exact same speed, because the direction is different, the velocity is different. On the first one, when you turn right, you might be going 20 miles an hour to the east, whereas when you turn left, you're going 20 miles an hour to the west. velocity includes direction. So that means that one of the cool things about velocity is that your velocity can change even if your speed stays the same. So if you think about a car doing laps around like a NASCAR track, right? And even if they like set their speed at 100 miles an hour and then put on the cruise control, which I don't think that they have cruise control in NASCAR cars, but if they did, let's imagine they do. If they're zooming around the track at 100 miles an hour, their speed is staying the same, right? It's always 100 miles an hour no matter what. But their velocity is changing because they keep changing direction. At first, they're going 100 miles an hour to the right, but then they have to turn and go up, but then they turn again and go to the left. Then they have to turn again and go down, and then they turn again and go to the right. So their direction keeps changing, so their velocity will keep changing. So because of this, because we also are keeping track of direction and how an object is moving when we're calculating velocity, that means that the average velocity of an object isn't just the distance over time. For velocity, it is the displacement over time. So how far away from the starting point are you getting, divided by how long it's taking to reach that distance. So your average velocity, instead of being distance over time, it is displacement. What is your total distance away from your starting point? So just with displacement, if you travel a large overall distance like that NASCAR car that's going 100 miles an hour for hours and hours around that track, doing hundreds and hundreds of miles at that time, if you end up where you started, you have no displacement and therefore zero average velocity. So if your displacement is zero, that means your average velocity is going to be zero as well. Because if you remember from your math classes, 0 divided by any other number is equal to 0. So if you're calculating average speed, you just have to look at distance, how far something traveled. If you want to calculate velocity, you have to look at how far did it travel from its starting point. What is its total displacement? All right, so there are some questions on the homework that I'll show you guys at the end of the day today, where their distance might be changing a whole lot. They might be doing a lot of distance in some of the examples, but their displacement may not actually be that large. So average velocity isn't just distance, it takes into account displacement divided by time. So if you spend a lot of time going really, really fast, but you end up at the exact same point as you started at, you're still going to have zero velocity. All right. So speed and velocity always get people a little bit tripped up because when you first hear these terms, you've probably heard them used to mean kind of the same thing. And they are very similar. They both measure how fast something is moving. Again, the main difference between them is that velocity includes the direction of the motion. The car is moving 5 miles an hour to the east or to the north. So for velocity, you have to have that direction in there as well. So velocity is linked with displacement, how far away you're getting from your starting point, right? Because that direction tells you the direction that you're going from the starting point. So the further away from your starting point you get, your greater average velocity, because you have a greater displacement. So speed and distance go nicely together. Velocity and displacement go right together. And again, in order to figure out displacement, you have to figure out how far away is the ending point from the starting point. There may have been a whole lot of like back and forth movement in between. They may have covered a lot of distance, a lot of ground, but displacement is all about just looking at that starting and ending point. So a lot of times people like to graph the speed of something, kind of see how quickly is it traveling over time. And remember, speed means looking at distance and time. So that's how people graph speed as well. How far away or how far are you traveling? And how much time has it taken you? So right here we have some time where we're getting further and further away from, or we're traveling more distance over a certain amount of time. So we have a certain speed right here. Then when the line goes flat, that means that even though time is going on, there's still seconds ticking away. The distance is not changing. So this is what happens when your object is stopped. So if something is not moving, the distance is going to stay the same. It's not going to be covering any more distance, even though time is still ticking on. So imagine that you're traveling at like a certain speed, but you come up to like a stoplight. And so you have to slam on your brakes. You sit there for like 10 or 15 seconds or so, not moving at all. And then eventually the light turns green, and so you can start going again. So notice that right here we have a little bit of a faster speed because we're covering a lot of distance in a certain amount of time. Over here we have a slower speed, right? This line is not as steep. It's not going up as quickly, which means that it's taking a longer time to cover a certain distance. So if the distance goes down and the time goes up, that means our speed is down as well. So if you look at a graph that has distance and time on it, that means that they're graphing the speed of some sort of object. Maybe it's moving quickly and it has a steep slope. Maybe it's moving more slowly and it has kind of a more gradual slope. Or maybe it's stopped, in which case its slope will be totally flat, since the distance doesn't change when something is not moving. So again, the steeper the slope, the greater the speed, because it means that you're traveling a further distance, right? Your line is going up faster, so your distance is going up faster. If your distance is going up slower, you're traveling distance over a longer period of time. That means that your speed is going to be lower. So the steeper the slope, the greater the speed. That also means that the more gradual the slope, the smaller the slope, the slower the speed. So again, if you want to calculate the speed of something, that's when you use distance divided by time. So there are a lot of these really simple kind of physics equations where it's just the three different measurements. And in order to help remember how to calculate them, sometimes people like to use these little formula triangles. right here, formula charts. And so the way this works is that you cover up the unit that you're looking for. If you had it like on a piece of paper, you could like put your hand over it. On a computer screen, you just have to kind of mentally block the unit that you're looking for. And then the chart will tell you what sort of measurement to do or what sort of calculation to do. So if the two different measurements are on different heights on the period, like one is above and one is below, then you use division. If they're at the same level, then you use multiplication. So that's what the little thing is showing right here, is that if you're doing D and S or D and T, you're going to use division. And if you're doing S and T, you're going to use multiplication. So again, how it works is, say you want to calculate the time that something took. So you would cover up with your hand, or just picture that it's covered up with your hand, the time part of the triangle. And then you have distance on top and speed on the bottom. So this would mean that if you're looking for time, you do distance divided by speed. Same thing if you're looking for speed. If you cover it up on the triangle, and then you do distance is above time. So you do distance divided by time. And then finally, if distance is the measurement you are looking for, then you cover that one up on the triangle, and you have time and speed next to each other down here. So distance is equal to time multiplied by speed, or time times speed. So some people like having it there, some people don't. I just like to introduce it to you guys just in case that you find it helpful. Instead of having to remember 3 different formulas, if you can remember this one triangle and how to use it, then that's all that you need. Again, we looked at this a little bit earlier, where if you know 2 of these measurements, if you know distance and time, or you know distance and speed, or you know time and speed, then you can use one of these formulas to calculate the other 2. And there are some questions on the homework where it gives you 2 of these measurements, and you have to calculate the third one. So you may have to calculate time, or calculate speed, or calculate distance. So say, for example, we have a sailboat that travels 120 meters in 60 seconds. And it wants to know what is the speed. So this problem is asking, what is the speed of the boat? It wants to know how fast is the boat traveling if it moved 120 meters in 60 seconds. So if you remember from the slide that we were just looking at, speed is equal to distance divided by time. So our distance in this case is 120 meters, because meters is used for distance. Our time is 60 seconds, because seconds are used to measure time. So speed equals distance over time. Distance is 120, time is 60. Speed equals 120 divided by 60, which is 2. So the boat is traveling at 2 meters per second. And so now I want you guys to think for a second about this next question. What is the speed of a car that takes 3 hours to travel 150 miles? I'll give you guys about 30 seconds to a minute or so to think about it, and then I want somebody to see if they can tell me the answer. So a car has traveled 3 hours and gone 150 miles. What is its average speed?
It's 5 miles per hour.
Close.
50.
Yes, Dennis is correct. 50. So Frishta, you are on the right track.
Oh yeah. Sorry, I forgot the zero. Yeah,
Hey, there you go.
50.
No worries. So the car had an average speed of 50 miles an hour. Because speed is distance over time. So if the distance is 150 miles and the time is 3 hours, then our average speed is 150 divided by 3, which is 50. 50 miles an hour. Miles an hour for 3 hours, you're going to travel 150 miles.
Yeah.
All right. So simple stuff, but really, really important when it comes to calculating this type of speed. All right. So the last thing that I wanted to go over with you guys tonight is acceleration. So acceleration is related to speed and velocity, but acceleration is measuring how much the velocity of an object is changing. So if the velocity goes up or the velocity goes down, that means the object is accelerating. So there are two different ways that we can change velocity, as we just talked about. Velocity has to do with speed and with direction. So if we change how fast something is moving, or we change the direction that it's moving, that changes the velocity, which means that we have some sort of acceleration going on. So acceleration happens when we change speed, when we change direction, or if we change both things. So normally, if you think about accelerating, like a car that's accelerating, you probably picture somebody stomping on the gas pedal and the car shooting off after the light, or like seeing somebody blow by you on the highway, right? So most people, when they hear acceleration, they think speeding up. However, acceleration also refers to slowing down. So just like velocity, acceleration has direction. So if you are reducing your speed, that is another form of acceleration because you're changing how fast you're going. And acceleration is all about change. So while most people think of acceleration as speeding up, acceleration could also refer to slowing down. So if acceleration and velocity are in the same direction, if a car is accelerating to the right and it's increasing its velocity to the right, so the car is traveling to the right and it's also changing its speed to the right, then the acceleration is positive. So the speed is increasing because the acceleration and the velocity are both going in the same direction. So this would be a car hitting the gas once the light turns green. On the flip side, if your speed is going down, if your acceleration is decreasing, that means that your acceleration is in the opposite direction from the velocity. So the car is moving to the right, but when you hit the brakes, all that friction in the wheels that is stopping your car is causing it to accelerate to the left, essentially. And so because your acceleration is in the opposite direction of your velocity, the speed is decreasing. So even though the car is traveling to the right, its speed is going down. And so this means that its acceleration is negative. It's having a negative change in speed. So if you're in your car and you're moving up to get in front of somebody, or you're slowing down to get behind them, you are accelerating. If you're a water skier and the boat stops, or you let go of the rope, then you're going to accelerate. You're just going to accelerate negatively, or some people refer to it as de-acceleration or deceleration. So that just means slowing down. Your speed is going down. A softball or a baseball, somebody may have threw it, the pitcher may have thrown it at the batter at 60 miles an hour, and then the bat hits it, and now it's traveling 60 miles an hour out of the stadium, right, if you're hitting a home run. So its acceleration changed, even though the speed may have, for the most part, stayed the same, because the direction of the ball changed. It started going this way, but then it very quickly started going this way. So because it had that change of direction, that means that it had a change in acceleration. We changed the direction of the ball. So acceleration is all about change. Your speed going up, your speed going down, your direction going from this way to that way. All of it in science is referred to as acceleration. Either your acceleration is going up or your acceleration is negative and changing down. So acceleration is the change in velocity over time, right? Because we have some sort of change in speed or direction. So the simplest way to calculate acceleration is to look at the final speed of an object minus its initial speed. So what speed did it start going? What speed did it end up going? And how much time passed to go from start to final speed? So that is kind of the simplest way to calculate the acceleration that an object goes through. Final speed minus initial speed over time. So it's change in speed divided by how long it took that change to happen. All right, if a car goes from 0 to 60 miles an hour, if it did that in 6 seconds, then that would be incredibly fast, right? If it did that in 6 minutes, that would be really slow. So acceleration is all about how long did this change in speed take. The higher the acceleration, the bigger the difference in speed, and the smaller amount of time it took for that change to happen. So roller coasters are really great examples of changing and calculating acceleration. So this particular roller coaster example, it's at the top of a slope and it's just starting to go down at 4 meters per second. And then when it hits the bottom and goes through that bottom of the slope, it is clocked in at going 22 meters per second. So if we want to calculate the acceleration, we have to figure out our final speed, which is 22 meters per second, our initial speed, which starts at 4 meters per second, and how much time it took, 3 seconds. So we want to know acceleration. We have to do final speed of 22 minus the initial speed of 4 divided by 3. So if you remember back to your algebra days when you're doing the order of operations, you always do the parentheses part first. So you always, when you're doing acceleration, you always want to calculate the change in speed first. So you do 22 minus 4, which as it turns out is 18, divided by 3. And 18 divided by 3 is 6. So the acceleration of this roller coaster is 6 meters per second squared. So acceleration is kind of a weird unit of meters per second squared. Essentially, what that means is 6 meters per second, which is a fancy science way of saying every second that this roller coaster was accelerating, its speed increased by 6 meters per second. So it started off at 4, and then 1 second later, it was at 10, and then 1 second later, it was at 16, and 1 second later, it was at 22. So each second that passed by, our speed went up by 6 meters per second. And that's what this meters per second squared refers to. How quickly is our speed changing? So just like with speed, we can also graph acceleration, only this time, instead of having different distance on the y-axis, we have speed. So how fast that something is moving. So if our line is going up, that means that our speed is going up. So our object is accelerating in a positive direction. If our line is going down, that means our speed is going down, which means that our object is accelerating in a negative direction, or it's deaccelerating, it's losing speed. And if the line is flat, that means, it doesn't mean that we're stopped, because remember, this is speed that we're looking at over here. So if something was stopped, its speed would have to be 0, which means it would be down on this line right here. This line means that we still have a certain amount of speed, but it is not changing. The speed is staying the same. So we're not accelerating, we're not decelerating, we're maintaining a constant speed. So that's why this line is flat right here, because our speed is not going up, it's not going down, it's staying the same. So maybe you're at a stoplight right here, and then it turns green. So you accelerate for a little bit to get up, and let's say you're on kind of not a highway, but like a frontage road or something. So you accelerate to 40 miles an hour, and then you hit that, and that's the speed limit. So you're cruising at 40 miles an hour for a little while, but you can see up ahead in the distance that there's a red light happening. And so you start to slow down your speed. You hit the brake and start to decelerate or negatively accelerate your car. So that's what these acceleration graphs are meant to show. If it's going up, we're accelerating, our speed is increasing. And again, just like our speed graph, the steeper the line, the faster, the bigger the acceleration. The shallower the line, the slower the acceleration. If the line's going up, we're speeding up. If the line is going down, we're slowing down. And if the line is staying flat, that means that we're moving at a constant speed. You hit cruise control, and now you're cruising at 50, 60, 70 miles an hour, depending on what kind of road that you're going through. So acceleration is all about this change, changing the speed or the direction of an object. If our speed is staying the same and not changing, that means that there's not any acceleration that is happening. All right, so does anybody have any questions on acceleration or speed or velocity so far?
No, sir.
All righty. So the last thing that I kind of wanted to do with you guys this evening was go through some of the questions on the homework and kind of take a look at how they're set up and information that you need in order to answer them.
Excuse me, sir. We have two homework. They are the same. I think they are the same. We must do both of them, or one is enough?
Nope, just one is enough. So I give you the two options because some people like doing the homework on the Google form like this.
Okay.
But other people, that doesn't work as well for them, and they still like doing it on Google Doc like this.
Okay.
So that's the exact same homework with the exact same information and questions. It's just presented in a different way in order to make it easier. But you only have to pick one and do whichever one works best for you.
Okay, thank you.
No problem. So up here, the first part, I have just a little bit of reminder of speed and velocity, where average speed is the distance divided by the time, and the average velocity is the displacement divided by the time. And so the first sets of questions on here provide you with some different scenarios and then ask you about things like average speed and average velocity. So on our first one here, we have your house and a friend's house that are 3 miles apart from each other. And you run 3 miles in half an hour, and then you walk back home 3 miles, which takes you 1 hour. So when you think about this problem, again, we have to remember distance, displacement, and time. So if it's 3 miles from your house to a friend's house, and you walk there and back, what is the total distance that you have covered in this trip?
0.
Close, but remember, distance is just how much ground that you covered.
Okay, so that would be the 3.
So it's 3 miles from your house to your friend's house. And if you walk from your house to your friend's and back to your house, what's the total distance that you covered?
10.
6 miles.
Not 10, 6. Exactly. 3 miles there plus 3 miles back means 6 miles in
We have to
total.
get better on that. Good.
Then what I think Frishta was talking about earlier, if you start at your house and you go to your friend's house and you come back, what is your total displacement?
So that would be 0 when it's displacement.
That would be 0. Exactly. Because you started and ended at the same place, your house. And if your starting point and your ending point are the same, you have 0 displacement. So if it took you 30 minutes to go in one direction and 1 hour to go in the other direction, then how many total hours did you spend walking?
1 hour and 30 minutes.
And how long is 30 minutes compared to an hour? Like what percentage of an hour is 30 minutes?
Oh,
Half.
15%.
Yeah, 50, right? 30 minutes is the same thing as half an hour. So these down here wants you to calculate it in hours. And so it took 1.5 hours or 1.5 hours trip, right? Half an hour there and 1 hour back means 1.5 hours in total. So you'll use those measurements that we just talked about in order to calculate the average speed of this person and the average velocity of person. So up next, we have a little skier down here. And the skier is moving back and forth across this track right here. So the track has the numbers laid on it, kind of like a football field, only in meters, not yards. And so he goes from A to B to C, then to D. So it goes from 0 to 160 from A to B, 160 to 120 from B to B, or from B to C, excuse me. He goes, I'm going to start over. You start at A, you go 160 meters to B, and we go from the 160 mark back to 40 for C, and then we do another 40 to 120 to B to D. So on this one, if you want to know the total distance, you'll have to add up how far did they travel when they went from A to B, plus how far they went from B to C, plus how far they went from C to D. Remember, distance is just the total amount of ground covered. So you have to add up from A to C
350.
to D, how far did they go?
350.
Then it says 350. So 0 to 160 is obviously 160. And then what's the distance between 160 and 40?
120.
120. And then what about 40 to 120?
100.
Close, but not quite. 40 to 140 would be 100, but what's 40 to 120?
80.
80, precisely. So we've got 160 plus 120 plus 80. And that gives us our distance, our total distance. And then velocity, remember, is our displacement. So for velocity, you just have to look at what is the distance between the starting point and his ending point. So in this case, his starting point is A, ending point is D. And oh, I just realized there's a typo on here. That should not be miles an hour. But anyways, so for the average speed, you have to add up all of those distances that he's covered and by how many minutes. I think for both of them, it's 3 minutes total. And then for velocity, you just have to look at the starting point and the ending point. What is his total displacement from start to end over those 3 minutes? All right. And then next one is a graph of a 100-meter race. So Donovan Bailey ran 100 meters in 9.84 seconds. So on our little graph here, we have his markings for each one of the 10 meters. So at every 10 meters, they measured how much time it's taken him to get there. And so his final measurement was 9.84 seconds. He covered 100 meters. So the 9.84 here is his time, and the 100 is his distance. So this one should be a pretty straightforward average speed calculation. And then the final three questions down here, number 6, 7, and 8, are all different types of speed calculations. So for the first one here, very similar to what we've already been looking at, where it's a problem dealing with trains, and it tells you that they can travel 155 miles in half of an hour, and wants you to figure out their average speed in miles per hour. That's our speed equals distance divided by time. Number 7 down here talks about a guy skydiving from an extremely high altitude. And it tells you that he fell 19.5 miles and he averaged 254 miles per hour. And then it wants you to calculate how much time did it take. And so you have to know if his average speed was 254 and the distance was 19.5, you'll have to calculate how much time did it last. And then finally, we have a question relating to hummingbirds that can travel very, very quickly, about 28 miles an hour. And they even go through this crazy long journey across the Gulf of Mexico, where they fly for 18 hours straight, which is way too much flying if you're a tiny little bird. So it's amazing that they can do that. But regardless, this is one where it wants you to calculate the distance of this journey based on their average speed and the amount of time that they spend flying. So these last three questions all have to kind of do with manipulating that speed equation in order to calculate either speed or to calculate time or to calculate distance. All right, so does anybody have any questions about these homework problems?
Can we do these assignments tomorrow, or it's for today?
This is the assignment for today. So since you guys are in this call right now, you already have earned your attendance credit for today by being in the class. So if you aren't able to turn this in until tomorrow, that is totally fine, and it will not affect your attendance for today because you already got your attendance by being in class with me here tonight.
Okay, how about the grade? An effect on our grade if we do it tomorrow?
Nope.
Okay.
You don't get any points taken off for having it be late. It doesn't really matter to me when you get it turned in, as long as you get it turned in at some point before the end of the term.
Okay, thank you.
Hey, sorry, Mr. Stanley. I had my phone had died in the middle of that.
All right. Thanks for popping back on. And it still record through all of the stuff that we went over with the homework. So if you want to go back and rewatch some of the part that you missed later on, and you're more than welcome to do so.
Okay, great. Thank you.
No problem. So yeah, again, since you guys are all here tonight, you already have your attendance counted for today. So feel free to take your time on this assignment and go back to the notes and go back to this video if that helps you figure out some of the questions. Also, as always, you can always reach out to me if you're having any issues with any sort of assignments or understanding anything, and I'll be more than happy to set up a time to help you out.
Okay, sir. Thank you.
No problem. Does anybody else have any questions about the notes or the homework or anything that we have talked about here this evening?
No, sir.